Okay, so now we're going to take a look. Oops, let me get my, excuse me for a second here. There we go. So there's been a term that we've been throwing out there, and your textbook has it, and you might have heard it before, but the tangent line problem is a process in calculus that we refer to as differentiation. So when you hear differentiation, what we're saying is differentiation is the process that finds the derivative or the slope of the tangent line or the instantaneous rate of change. Those important ideas of what it is we're doing. Okay. Now, there's a couple of different notations for this. One of them you're going to see that makes a lot of sense, but I don't know if it's because it's got extra letters that people don't like to use it, but usually this is the first way you see it. Okay, so this here, it's usually read as f prime. So if you were to say this next year in university, you would say to your professor f prime of x, the first derivative of x. Okay, and that's usually the notation that you're going to run into for most of this unit. However, there's going to be times in our class where another notation makes a lot of sense too. And that's this one here. Now, as far as I know, this comes from Leibniz, and the other one comes from Newton. So both good ideas for representing what they were doing, but this one here is what we would do. I believe this was Leibniz notation. It's more specific, so what it means is the derivative of y with respect to x. So what does that mean? The derivative of y, that means the rate of change in y with respect to x. Like that parabola, the value of x determines how fast you're changing. So it's with respect to x. And we're looking for the derivative of y. So it's more specific. You'll see it makes a lot of sense when we get to a couple of units where we're talking about rates of change in both x and y. But for most part, we're going to use the first notation. Okay, so I'm going to have you use the limit process, try and find the derivative of x cubed plus 2x, and just to help save you some math time, here is the expansion for x cubed, okay? And then when you finish that, see if you can find the derivative for 2 over t, okay? Okay, so I'm going to catch up to you on the first one here. So let's see here. If this was my first function, it's going to be this one here, plus 2x plus 2 delta x. So I'm just cheating a little bit so I don't have to write as much up on the board. And then I'm going to take away x cubed minus 2x. Well, I guess I could do it this way. Okay, so that would be the expansion. If you've done the expansion of this and we're trying to collect up and simplify our like terms, then what I get left over would be 3x squared delta x plus, let's see here, 3x delta x squared plus delta x cubed plus 2 delta x. Sorry, plus 2x first. Then a 2 delta x. Okay, these pieces, oh sorry, those pieces I was right the first time, sorry. It was 2 delta x because these pieces are going to end up canceling out. So that's what I was left with. And underneath it, I have delta x. So if I factored out the delta x, the piece that I'd be left with is 3x squared plus 3x delta x plus delta x squared plus 2. And remember, delta x is going to 0. So that means this 0 times any number is 0. 0 squared will be going to 0. So what I'm left over with is 3x squared plus 2. So if I wanted to know the slope, let's just see if we're on the right page here. If I want to know the slope of the tangent line at x equals 2, what will it be for x cubed plus 2x? $14, because I would substitute in x equals 2 to here. So if I want to know on the graph when x equals 2, that's the rate of change at x equals to 2. Okay, so try the next one if you haven't already, 2 over t. Okay, so I'm gonna do this one on the next on a new page just so it's bigger and easier for you to read. I realize I've kind of crammed my space in there, but your definition, well, this one's in terms of t, so it doesn't. I mean, I'm certainly happy if you can do this in terms of x, but the variable we were given was t. That was what we were working with. So I'm going to do this in terms of t. So if you set it up, it should be t plus delta t. Take away 2 over t, and delta x on the bottom. Now, oh sorry, just said what I was not supposed to do. Okay, so if you had an x there, if you used x instead of t, that's fine, but the function was a function of t. So that means when we get an answer, this will be in terms of t, which is connected back to the function. So my suggestion was that you look at the fractions and how you might simplify this. So I'm going to times the top and bottom to get rid of those. I'm going to times it by t and t plus delta t. That's going to get rid of my fractions. So that's going to give me the limit as delta t goes to 0. And I'm going to have a 2t take away 2t plus delta t. It's so hard to get away from writing x, isn't it? Okay, 2 plus delta t. And on the bottom now, I have delta t, and I have t, and t plus delta t. Okay. So those are all the pieces, but now I've got my fractions are down to just 2. So let's try and simplify this. This would be the limit as delta t goes to 0. The top will be 2t minus 2t. Sorry? Oh, I did it again, didn't I? Delta t. Okay, sorry. There's something, I guess it's like there's some kind of emotional scar there that for something in math, it has to be an x, doesn't it? Okay, well anyways. So minus 2t minus 2 delta t. And then on the bottom of this, I'm going to have, let's see here, a delta t and a t and t plus delta t. Okay, so these two pieces would cancel each other out, and I would be left with the limit as delta t goes to 0 of negative 2 delta t over delta t times t plus delta t. So the problem that we were getting to divide by 0 was because we were multiplying by 0 with this delta t, but those two pieces will cancel each other out. So will this one, it will become a 0. So what I'd be left with then is negative 2. And can anybody make out what that denominator is going to result into? T squared, yeah, good. That's excellent. If you got that far with it, that's a tough one, especially if it's your first day working with it. Okay, so that means the instantaneous rate of change, what would it be when t equals to 1? Negative 2. Good. Okay, so if we were looking at the slope of the tangent, is this down from your point of view? Right? Is that down?
It's up.
That's up? Oh yeah, it's the same way. It's just, never mind. Sometimes left is right, right is left. But up is still up, down is still down. So, yeah, so it's going down.
That's going up.
Well, my elbow's, anyway, okay, let's try this side. Is that better?
Yeah.
Okay, so it's going down, and it's at a rate of negative 2. So this might be kilometers per hour. It might be something like, people per day or, dollars per month. Who knows? But that's excellent. So now what we're going to do is we're actually going to find the equation. So we're going to go one step further. So see if you can find the limit with the square root graph. Okay? And what I want you to do is I want you to go one step further, and I want you to tell me what's the equation that would draw the tangent line at 1, 1. So not just, oh, Mr. Joyce, this rate of change is 3. I don't know if it's 3. But the equation is 3x plus 2, and that will draw the tangent line on the graph. Okay? So start with the definition of derivative, and then we'll try to catch up. Hopefully that makes sense. Okay, so this is hopefully where you were able to come up with, is we were able to go the limit as delta x goes to 0 of square root x plus delta x, take away x all over delta x. And somebody already mentioned it, but hopefully this was the strategy that you decided on. Okay, so if I apply the pattern for the difference of squares, it's going to make life a lot easier. That's going to be the limit as delta x goes to 0. The top is going to be x plus delta x, and then take away x. That's all that's left for the other side. And on the bottom, I'm going to have delta x times the square root of x plus delta x plus root x. Okay. So if we keep going, this is the limit as delta x goes to 0. It looks like the only thing that survives on the top is a delta x, and that's a good thing because then it'll factor out on the bottom. So what do I have here? Sorry, there should be, no, that's right, and this should be x plus delta x plus root x. And those would cancel each other out. So we can now figure out this limit. So there'll be 1 over this piece is going to 0. So it'll be 1 over root x plus root x, which would be 1 over 2 root x's. So that's the derivative. We could figure this out at any point. The one that we're interested in is at the point 1, 1. Okay, so x equals to 1 here. So if I wanted to know the slope of this line, the slope is going to be, using the derivative here, 1 over 2 root x, which is 1/2. So now I know where the slope is. If you've forgotten the point slope of a line, that's the way to do this here. It's going to be y minus y1 equals m times x minus x1. And here's the point right there. So I have a point and I have a slope. So that's going to be y minus 1 is 1/2 x minus 1. So y equals 1/2 x minus 1/2 plus 1. So the equation of the line here will be 1/2 x plus 1/2. So let's verify it with the picture. I'll come back to that screen if you're still copying it down. But the original graph was y equals square root x. Okay, and let me zoom in a bit on this. Let's go. So the equation that we've predicted is 1/2 x plus 1/2. Bam, right there. Okay, so that equation is exactly the tangent for the square root graph. We've been able to calculate this now. Okay, so that's the end of our first part.